This is part 2 of chapter 3 lecture. We're going to deal with Bohr's atomic model and electronic structure and how to draw electronic structures for every element and ion in the periodic table if we need to. These will cover sections 3.2 through 3.4, so read these as well as listening to or watching the video of the lecture because it will help you to read it in the textbook as well. When we last talked about the model of the atom, we talked about how we knew, so 100 and some years ago, physicists and chemists, they knew that the atom was now divisible, divided into even smaller particles, and we knew that those particles were protons, neutrons, and electrons. Protons were positively charged, electrons were negatively charged, and neutrons did not have a charge at all. Protons and neutrons made up the nucleus of the atom, and the protons and electrons had to be an equal number for a neutral atom to cancel the charges. Now some of the models, the initial models, we talked about those, were that you had this large sphere in the center of the positive charge and then the negative charges orbiting around. Well, what happened from this model, from the gold foil experiment, Rutherford figured out that, and his team, they figured out that it really, this model wasn't quite exactly right. And what they came up with was that in the center, it's the very dense nucleus, and the nucleus is made up of the protons and the neutrons, and then the electrons are orbiting around. Now the orbit, if the electrons are orbiting around, they have a very clear path and a very defined path. So if I have one electron orbiting over here, another will be orbiting this direction and another that direction, etc., etc. However, what experiments were showing and what calculations, mathematical calculations were showing even later on, was that the electrons didn't really follow a very, very specific, well-defined orbit like the planets do around the sun or like the rings of Saturn, etc., etc. In fact, at any given time, the electron might be around here, but it might be over here, or it might be over there, or it might be all the way over here. So it doesn't really follow a very well-defined path. The mathematical calculations that were being developed alongside with the experimental data were showing that really the electron has a probability of being around. So we cannot really say for sure that the electron is right here at this moment in time. But we talk in terms of probability, that there's a probability that the electron might be in this sphere over here, which would be the closest to the nucleus. If the nucleus is right at the center here of these intersecting lines, then these dots around here that forms, it's a three-dimensional, so which would form a sphere, that would be where the electron could be found 90% of the time. Now, it could be over here or it could be over there within that sphere. I'm not exactly sure where, but this is the probability of where it could be. Now, in some cases, it might be over here or over there, but most of the time it would be found in this particular sphere, which ended up being called a shell. These shells that we're going to talk about are also called energy levels or orbitals, okay, energy levels. And the one that is closest to the nucleus, that is the first energy level, where the electron that has the lowest energy resides. Now, if I took the model of the hydrogen atom that only has a proton, doesn't have a neutron, and it just has one electron, that electron has the lowest energy that it could possibly have, and it is found about 90% of the time right around that proton in this sphere over here. But what happens if I give that electron a larger, so if I give it a little more energy, okay, this is the lowest energy, but what happens if I increase the energy of that electron? This is done typically when the electrons absorb light of some form, a photon of light, and it has to be a very specific energy, and I increase the energy of that electron. It just has to be very specific, however. It can't just be any value. Well, I would find that the orbit of that electron is going to change a little bit. It might now be a little farther from the nucleus. Obviously, the closer to the nucleus you are, the lower the energy. The further out you are, the higher the energy. So if I increase the energy of the electron, it might be found, instead of this sphere, it might be a little larger sphere. So it might be found over there. So now it has two probabilities. It could be found in the middle, but it could also be found in another shell. And that is in another energy level. So I'd have two energy levels that it could be found in. And if I kept increasing the size or the energy of that electron, I'd find that it would find different shells that it could belong to. And some of these, they will not all be spherical. Some of these would be spherical and some would look like dumbbells. It is just the shape, the higher the energy of the electron, the more intricate the shape of the orbital that it would be in. But once again, these are probabilities of finding the electron, because we cannot really say for sure that the electron is right here at this particular time. Now the person who really described the modern model of the atom was Niels Bohr. And he postulated that these shells, these energy levels that we've been talking about, have very, very distinct energies. And an electron cannot go from one shell to the next or one energy level to the next without absorbing some energy. And it has to be the exact kind of energy. It cannot be from halfway, for example. The idea that comes to mind when we do when we talk about energy shells is like moving a book from a bookshelf, from one shelf to the next. In order for me to move a book from shelf 1 to shelf 2, I have to raise it a specific amount. I cannot do it halfway or it will not go into the next shelf. It will just fall back into the same one. I cannot give it too high over here, because it cannot go it will fall back down. So it has to be the exact same difference. So it has to match the difference in energy level from 1 to 2. This has a number. So this energy has a number that is associated with the first shell. And then the second shell has an energy that has a number 2 that is higher than the first. If I want to move an electron from the first shell to the next, I have to give it exactly the same energy as the difference between these two. If I don't, then it will not move to the next shell. This is what quantized means, meaning very packet. So I have to give it an exact packet of energy to move from one to the next. Same thing with going from a first step to a second step. You have to lift your leg exactly the same height to move from the first step to the second step. If you don't, you will not get to the second step. Same idea here for first and second and third shells. Now, if I promote, we call that promotion. If I promote an electron to a higher level by adding a certain amount of energy that's equal to that difference, it will stay there for a while, but then eventually it will give off that extra energy in a form of light. And we can, if it's in the visible spectrum, we can see these these energy differences in a form of light. For example, this is for hydrogen. We can see these jumps, if you will, from one level to the next with different colors. And we can say that, oh, if I move it from one to the second, because this is the smallest energy difference, this will be the highest lambda, the highest wavelength, which is the red wavelength. If I have an, an electron that moves from the first level to the third level, and then it moves back down, this is a higher energy difference, which means it will be a shorter, because they're inversely related, a shorter wavelength, and I move to the left of the energy spectrum. So I move from the red towards the yellows and greens and blues, and then all the way to violet. So depending on how large that energy difference is, I would be moving from the red all the way to the violet end of the spectrum. But we can tell that there's several levels, several transitions that an electron can undergo, going from one level to the next. It could jump from 1 to 2, or from 1 to 3, or from 1 to 4. And then if it jumps back down, it can emit these lights with a particular color, and we can tell by the color which transition it is, which jump from which level. The higher the jump, the bluer, if you will, or the more violet the color is going to be. The shorter the jump, the redder it will appear. Now, we talked about these, so this is a mathematical model of the probability of the electrons. We call these orbitals, and they can appear in three-dimensional. The simplest one is we call this the s orbital, the sphere orbital, and these are the lowest energy ones. Now, if we get to higher energy, so if we add more energy to that electron, these orbitals, these probabilities where it could be found, will change shapes, and they can take some pretty interesting shapes. And once again, these were calculated doing mathematical model, but this is what we go by. So we talk about the first orbital being an s orbital. That's the simplest one, the least energy one. But we also said that so if this is my 1s, my first level energy, and this is the first orbital, you can see if this is where at 0 is where the nucleus is, as I move further from the nucleus, I have this probability of finding the electron right around here. And then as I move even further, so about 25 is where, between 0 and 25 picometers is where I should be able to find that electron. And as I move farther out from the nucleus, it disappears for a while. However, if I have another energy level, so this was for this one and 1, but if I move to the next energy level, this one will have this sphere and this sphere. So we'll have two places, two probabilities, two spheres where I could find that electron. There we go. We have two spheres, two probabilities. Now, as I move, so I moved further here. This is between 0 and maybe 20 picometers. Now there's a probability in between these two levels that I cannot find the electron. Its probability is 0. So I have this curve, it goes to 0, and then I have a larger, so this is for the second level, this is the probability where I would find the electron. And you can see that as I add levels, you could add curves, and there it is. For the third 3s, right, this is the subshell. I have 1, 2, 3 areas, right? So this is my third shell. I have 1, 2, and 3 shells, or 3 spheres, where I could find that particular electron. And all of these have different energies, obviously. This is furthest from the nucleus, so this will have the highest energy. So this blob over here, this sphere, this is a little closer, so this will be in between, and then that's the closest, so it will be the lowest energy. Now, what we find is that these orbital the shells will change shape for every level. So if these are my first level, second level, third level, level 1 only has one particular shell and one subshell, which is the sphere, only the sphere. But when we go to the next level, level 2, it will have a sphere, but it will also have these other different, what we call subshells. This is a subshell of that level, level 1. This is a subshell of level 2, so level 2 has a sphere, but it also has different subshells. And once again, these are just mathematical shapes of the probability of where we would find the electron in three-dimensional space. And this is what would look like. So this is the s orbital, which every level has one. So level 1 will have 1, level 2 will have 1, 1 and 2, level 3 will have 1, 2, 3. But level 2 will not only have the S subshell, it will also have the P subshells. So that electron in level 2, which was here, that electron, if I give it enough energy to put it in the second level, it could be in a sphere subshell, but it could also be in what we call the P subshells. They look like dumbbells, and they are in the X direction, so the horizontal, vertical, and then this in and out of the plane of the paper or the computer. So in 3 dimensions, and they have these dumbbell shapes, but they're all in 3 dimensions. So the probability of that electron being, it can be in this subshell or in these subshells too. And then when we move on to further higher levels, we can get some really interesting, intricate geometries of these orbitals. But just remember that these are just places where the probability of where the electron can be found. The first level only has a shell, and the shell is the subshell. It is the same one, the same thing. It's the simplest one. Level 2 has 2 subshells. It has an S, which is a sphere, and it has these P ones, which are dumbbell shaped. Level 3 will have 3 subshells. It has an S, the P, and then the Ds. And these individual ones then are called orbitals. So there's 3 different ways to look at it. The level, with the energy level, the subshell, and then the orbitals, which are individual geometries. Okay, now we have to learn to how to write the electron, to put the electrons in a specific pattern of energy levels for a particular atom, because they follow, so the electron orbitals and how they are filled, they follow a specific pattern, and we have to learn how to do that. For example, my lowest level, my first level, we said only has one shell, one subshell, one orbital, and it's the same one, it's the sphere. That's the simplest way. So I will find the electron, if I only have the first electron that I have will fit into this sphere. If I increase the energy, it might go into the second level, but most of the time it will be found in this shell over here. If I add another electron, it will also go into this shell. But then if I add more electrons, so if I have, let's say if I go down the periodic table, as I increase in number of protons, I also increase the number of electrons. Well, those electrons have to be distributed somehow around the nucleus, and they follow a specific pattern of energy levels, and we're going to talk about how they are filled. But if I have 3 electrons now, I cannot fit it into this one because it will repel. These 2 will be matched in spin, we call them matched in spin, and then if I add another one, those 2 electrons will not make any more room for more electrons to fit in there. So it will have to go to the second level. Okay, this level has the 2 electrons in here, but then the third one will have to go to this outer sphere. If I add another electron, it will fit in here. So the 2s will have 4 electrons, 2 from the inner 1s and then 2 from the outer, the 2s. But then if I add another electron, it can't go in there anymore, so it will have to go into these. We follow once again a specific pattern of energy levels, and to do that we follow certain rules. And here are the rules. To write orbital diagrams, or how we fill those orbitals for specific atoms, we have to follow all of these rules. First of all, the first assumption that we make is that all ground state atoms, so all atoms, will have the same number of electrons as they do protons. This is nothing new. We're familiar with this because we know, we've worked problems on this. We know that if an atom is neutral, which means that the positive charge has to equal the negative charge. Now, these are the next 3 rules that we're going to follow. The Aufbau principle states that the electrons will fill from the lowest energy level first. So if we go over here, I will have to start filling the 1s orbital because that is my smallest energy. If you see this line over here, in this axis I have energy and it's increasing as I go from bottom to top. So 1s is the lowest energy level. Then comes the 2s. Then these orbitals are part of the p subshell of the second level, and they're equal in energy. Do you see that if I draw a line here, they all have the same energy. So for these have the same energy, but they're a little higher than the 2s. So the 2s is the lowest of the lowest energy level for level 2, the lowest subshell, and then the higher subshell is the 2p. And the 2p has 3 orbitals, 1, 2, and 3. So three directions, 3 places where I could put that electron. And then as energy increases, I hit 3s. This is the s that has all s. So 1s, 2s, 3s, 4s, all of the s subshells will have a sphere, but they have sphere within spheres, right? The 1s has only 1, 2s has 2 spheres, 3s will have 3 spheres, 4s will have 4, etc., etc. But 3s is higher than the 2p. And then the 3p, the p subshells for the third level will be higher than the second level, and even higher than the 3s. However, when we go to the d here, the 3d subshells are higher than the 4s. Therefore, the 4s will fill first before the 3d. So look at it in the whatever comes first will be filled first. 4s, then we move to the d, 3d, then we'll go to the 4p because this is a little slightly higher in energy than the 3d. So the Aufbau principle tells us that electrons will fill from the lowest energy first, and then we keep going as the energy increases, whatever comes next. The Pauli exclusion principle tells us that each orbital can only hold a maximum of 2 electrons with opposing spins. As I said, we can only hold 2 here. The third one cannot go in here, it has to go to the 2s. So each of these lines is 1 orbital, and each of these lines can hold only 2 electrons, one with opposing spins. One is pointing up, one is pointing down. Then we have to move to the next orbital because this has 2 and is satisfied, so he has to go to the next one. And this will be one pointing up, one pointing down, etc., etc. So Pauli exclusion principle, the exclusion tells us that you can only fit 2 electrons for each of these lines, which represent each orbital. And lastly, Hund's rule tells me that if I have orbitals that have the same energy, I distribute the electrons in such a way as to maximize the number of unpaired electrons. So if I am placing electrons in the p orbitals here, all of these have the same energy level. So if I have enough to let's say I have two extra electrons to fit over here, I cannot put an electron up with a pointing up and one pointing down and leave these two empty. I have to put one up here and another one up here. And then if I had more, I would put another one up here. So I maximize the number of unpaired electrons because it's a more stable configuration for the atom than having a paired electron and then two empty orbitals. It would rather have all of these be occupied by one electron, and then we go back and pair them up. So these are the rules that we're going to follow, and I have made several videos on how to fill out these electron configurations. You will have 3 different ways of doing it. This is called an electronic diagram, and I've shown you how to fill this out. Then I've shown you how to do a full electronic configuration by writing the shorthand notation for orbitals. And then the last part is figuring out how to write the just noble gas configuration, where I replace part of these orbitals with a noble gas configuration. I know right now it doesn't mean a whole lot to you, but watch the videos where you look at the examples and it will make a lot more sense. So I have sodium, I have titanium here, and nickel. And then I do a couple of examples on ions and how to figure those out. These are very similar to this diagram over here. They're just slightly different. They look slightly different. They're more compact because they're not stair-step. They're just up on top of each other. But watch those videos, and if you have any questions, we'll be doing a bunch of these at during class time as well. But if you have questions, please bring them to class. Now, a cool thing about this is we can use the periodic table to tell us what level and what subshell and what orbital is being filled at what point in time. Remember that we talked about the rows that are actually period? Well, that tells me what energy level I'm on. So if I'm in row 1, I am in, or in period 1, that tells me that I am filling the level 1. And level 1 has only one shell, one subshell, one orbital. It's the same for level 1 is the same. And that means that I'm filling the 1s. And look at and we said that 1s, that shell can only hold 2 electrons. And here's my 2 electrons. Hydrogen is one, the first one, and helium is the second one. So my first shell, level 1, is filled with these 2 atoms because I have hydrogen is one, and helium will fill that first subshell. So hydrogen has 1s1 and helium is 1s2 because it fills that, it has 2 electrons and it fills the 1s shell. Now if we move on to row 2, period 2, that tells me that I'm filling the second level, energy level. The first two groups of the periodic table are filling the S subshell. The next group, so this block over here, which you can count it as 13 through 18 or group 3 through 8, these are filling the P subshells. Now, depending on which energy level you are, that tells you which S and which P you are filling. For example, row 2 is filling the 2S and the 2P. Row 3 is filling 3S and 3P, etc., etc. Row 4 is filling the 4S, but now we have to go through the D orbitals. So remember we said we have 3S, 3P, then we go to 4S because it's slightly less energy than the 3D. When we fill the 4s, then we have to go through the 3d. So this block chunk over here is filling the d orbitals, the 3, the 4, the 5, and the 6. And then the inner transition elements are filling the f orbitals. So it's interesting to look at the divisions in the periodic table, and they will tell you, the rows and the column will tell you exactly what level you are filling and what shell or subshell and what orbital you are filling. For example, if I look at phosphorus over here, I will say that phosphorus is in period number 3, so it is filling the third energy level. It already has filled the 3s, so it has a full 3s, 3s2, and then it's filling the p orbital, and so it's 1, 2, 3. It's got 3 electrons in the p orbital. This will, once again, will make more sense when you watch the videos of how to do the actual electronic configuration, but it's pretty neat to use the periodic table to actually tell which subshell you are filling and how many electrons do you have in each. And here's the same thing, but it's just a little easier to tell because it doesn't have the names of all the elements. These are filling, so group 1 and 2 are filling the S. Group 3 through 8 is filling the P. And then the transition metals are, or the D block, they're filling the D subshells or the d orbitals, and then the inner transition elements are filling the f orbitals. Okay, this concludes this part of the lecture. We will pick up on the periodic trends in part 3.